Hello, everybody. Welcome to the seminar on computational geometry and robotics. We are very happy to have today Irina Kostitsyna as our speaker. Irina is from TU Eindhoven, and she will talk about unlabeled multi-robot motion planning for disk robots. Before Irina starts, let me remind you that you can speak up by unmuting yourself if you have questions, or if you prefer, you can write it in the chat, and occasionally I will read your questions to Irina. So Irina, please.
Thank you, Danny. Hello, everyone. I'm happy to be here and to talk about multi-robot motion planning and some recent results that we have produced. I'm planning to speak a little bit less than 1 hour, so there is enough space for you to interrupt me and ask any questions if you have. So don't hesitate, please. I'll start my counter so I know how much I am talking for. Okay.
Irina, Irina, we don't see the screen itself. We also see some portion of another screen. We don't see only the slides.
Oh, okay.
I don't know if you intended it to be like this.
No, I intended you to see only one slide on the full.
That's what we see now. Now it's okay.
Okay, and if I do this, then you see it covered with something.
Right.
Okay, okay. I'm playing here with multiple windows. So,
okay.
Okay, I hope this is fine.
Yeah.
Okay, so let me start. Well, what is unlabeled multi-robot motion planning? I'll introduce slowly the concept. Well, first, let's talk about multi-robot motion planning. Let's say we have a bunch of robots in some polygonal domain, and we want to find a schedule or path to move each robot from their starting position to the target position. And here, the more brighter color shows the starting position, and the transparent color is the target position where the robots need to move. So let's say a valid solution here would be for the purple robot first to move to the target position, then maybe the green one, and the last one is the red one. And you can see that we're being careful here so that the robots don't intersect the boundary of the domain and also each other. Okay, so this is the labeled version of the problem, where each robot has a specific starting position and a specific target position. But we, of course, can say that, well, we have a set of starting positions and a set of target positions, and we don't care which robot goes where. So that would be the unlabeled version of multi-robot motion planning. So here we can basically match any starting position to any target position. And then in between, there is so-called K-colored version of multi-robot motion planning, where we have K classes of robots. And here I denote them with different color and also with a little bit different size, so they can also be different shape. Within each class, we are operating in this unlabeled setting. Any robot can move to any target position, but of that specific class. Right? Okay, and then to make our life more easy, we're gonna look at disk robots instead of any more complicated shapes. So again, for disk robots, we can look at the unlabeled version. Here, the brighter green is the starting position. The more transparent green is the target positions. And as well, we can just define the K-colored multi-robot motion planning for disk robots. So now we have 3 colors here. the purple, the green, and the red. And within each class, we have the same number of starting positions and the same number of target positions. The goal is to route the disks from the starting positions to the target positions within their class so that there is no intersections with the boundary or with each other. So this is the sort of the summary of the problem that we have. And we want to find some optimal schedule, and what optimal means, it of course depends on the application. But today, let me not even talk about finding an optimal schedule. We'll just talk about the existence of a schedule, and if we can find one, right, we can optimize it later. Okay, so I will talk today about two recent results. So there will be two parts of the talk, and I will start with the hardness of the problem. And this result appeared, well, has not appeared because of COVID, of course, yet, but was supposed to appear at the FUN conference this year. And this is a joint work with 4 of my master's students. Okay. First, let me try to introduce some of the known results on how hard it is to find schedules for multi-robot motion planning. And right now, we're gonna stick to rectangular robots. Rectangular or square, so 90-degree corners. Okay, so there is quite some history here. We start with 1984, where it was shown that if we pack a lot of rectangles in a big rectangular domain, then it is, in general, PSPACE-hard to reconfigure, to start with one configuration and decide if we can end up with another configuration. Okay, and of course, this is very similar to a lot of puzzles that exist, right? Like the sliding block puzzle or the rush hour puzzle. In the rush hour, we have also a rectangular domain with rectangles of size 1x2 and 1x3, and they are called cars, and they can only move along their longer side. So if we're looking at this purple rectangle on the top, it would only move horizontally, left and right. And the puzzle is to figure out if we can free one specific car and move it to the boundary of the rectangular domain and through the exit. Yes?
Can I ask a question? So these, if you are rectangular robots in rectangular domain result, can these rectangles also rotate or just translate?
No, they are just moving without rotation, translation for now. Yeah.
Thanks.
Yeah. Thank you. Good point. Okay, so then rush hour is known to be PSPACE complete for cars of size 2 and 3. And in 2005, Bob Hearn and Eric Demain, they came up with this framework of proving a lot of different puzzle-like problems to be hard. So it's called non-deterministic constraint logic. And using that framework, they proved a lot of different puzzles and problems being PSPACE complete, including the sliding block puzzle. So the sliding block puzzle, you can move vertically and horizontally, no matter what the orientation of your rectangle is. And also the rush hour, where you do have restricted orientation for each car. Okay. So in the second item, they sort of reproved the known result. And then using the same non-deterministic constraint logic, there was a sequence of different improvements. So the next result was to only restrict the cars to one size of 1x2. It's also known to be p-space complete. And finally, getting to square robots, so 1 by 1 cars. Of course, then you need to start considering obstacles, right? We need polygonal domains, because if you put a bunch of squares of the same size in a rectangular domain, of course, you can reconfigure them. Okay. And I will be referring to a lot of work by people watching this. So I'm sure that you will see a lot of maybe familiar pictures. Okay, so the square robots in a polygonal domain with obstacles, reconfiguring them is also known to be PSPACE-hard. And then the late, yes?
I don't see actually why, if you're in a polygonal domain, you can always do this. I can understand it might be easy, but if your domain is entirely full, then you can't reconfigure it, right? Or
right, but then the answer is simple. Then,
yeah, I know. Okay, yeah, sure. So it's always easy.
So you, of course, you want to leave a little bit of gap so that some of the blocks can be moved around. And then that's where the puzzle becomes interesting.
So that's like a bit like the 15.
Sort of like that, yeah.
Yeah, which is
I think that's a good example of a puzzle that is easy to solve.
Yeah, it's easy to solve, although I also get quite some problems with these things, but I think it's easy, yes.
Of course, 15 is a labeled version. We are talking about unlabeled version. But if you notice that different sizes of blocks and cars, that means that we are in a K-colored version of the multi-robot motion planning. Okay, so I think this slide shows the results for rectangular and also square robots. So it was, you see, it's a long way to prove that actually puzzles or a multi-robot motion planning for squares is also PSPACE-hard. Okay, but I wanted to talk actually about disks today. So let's see what we know about disks. And the result list is much shorter than for rectangles. And it makes sense because rectangles and squares, they can be placed nicely in a grid. And if there is not much flexibility in how these blocks can sort of wiggle around, right? Because the corners, if you do not line them perfectly, the corners will prevent from the robots to slide in the way that they wish. But for disks, it was known for a pretty long time that the problem is NP-hard if we are within a simple, even if we're in a simple polygon, but the hardness construction uses many different sizes of disks. And now today I will show you a result that it is actually PSPACE-hard to reconfigure two-colored set of disks. And two-colored set of disks, they will be different radii, and the difference in the radii will be only a factor of 2. So we have two sizes of disks in a polygonal domain. Now, of course, I will be using holes in the construction. And the proof follows the same general idea of non-deterministic constraint logic reduction. So if you are familiar with it, it should be very straightforward because all the list of previous results for these rectangular cases, they follow similar ideas. Okay, so let me first explain what non-deterministic constraint logic is for those who maybe see it for the first time. It's like a game or a puzzle. We start with a graph, a directed graph, and this graph has two types of edges, red edges and blue edges. Let's say red edges have weight 1, blue edges have weight 2. each vertex has degree 3, and we set a constraint on each vertex that it has to have incoming weight of at least 2. So it either needs to have 1 incoming blue edge or 2 red edges at least. Right? So so this is not a flow, there is no flow preservation. What you're counting is just how many arrows are pointing towards me. And I want this to be at least weight 2. Okay, and then the moves that are allowed to perform in this graph is an edge flip. Each edge flip still needs to satisfy all the constraints. After flipping an edge, all the adjacent vertices need to have the constraints met. So for example, here you can see that, maybe I can annotate quickly. If I can get the pen to work. Okay, so this edge has incoming weight 3, right, from the blue edge and from the red edge. And that is why I can flip the red edge around. So now the constraints are still met for this vertex. The vertex on the directly to the left, it's even more happy. It has incoming weight 4, but now because it has 2 red edges pointing inwards, we can also flip the blue edge. Right? So let's flip the blue edge now. Okay, so these are basically the operations that we are allowing ourselves, and the question is, can we, with a sequence of valid edge flips, change the direction of one specific edge? And this is proven to be PSPACE complete. Also, another version is to say if we have a starting state of the graph where the state is just the direction of each edge, can it be reconfigured into another state with such valid edge flips? Okay. So now this framework is surprisingly useful when trying to prove hardness of various puzzles, and especially puzzles that involve moving blocks. So let's see how it's done. Okay, so there is furthermore a restriction on the vertices. So we only need to consider 2 types of vertices in the graph. The problem still will remain PSPACE-hard. So we have an OR vertex or an AND vertex. And why are they called this way? Well, imagine that we denote 2 edges as an input. And for the OR vertex, the 2 blue edges, well, OR vertex has 3 blue edges, AND vertex has 2 red edges and 1 blue edge. The red edges and 2 blue edges of the OR vertex are going to be the input. So now what we have here is to flip the out edge of OR vertex, we need to flip one of the input edge, right? And the AND vertex on the other side, to flip the blue edge, the blue out edge, we need to flip both in edges. So this is just a way of looking at the types of vertices to make our life easier, a little bit more structured way. And having vertices with 3 red edges is not necessary. The graph only with these 2 types of vertices is still going to be PSPACE-hard to reconfigure. Okay, so now when we build a reduction for our block puzzles, we're going to replace each OR vertex and AND vertex with some construction. And in my particular case, I want this construction to also have some moving disks, right? Okay, so the dark gray area is the, let's say, the boundary or representation of the boundary. And each OR vertex and an AND vertex, it will be enclosed in a square area. I'm going to say that the edge is pointing, the directed edge is pointing inwards towards the vertex. If the disk, so there will be a specific edge disk shown in green here, is sticking out halfway from the square, and the edges are pointing outwards if the disk completely fits inside the square area. So it's the same for OR and vertex. So what happens if we try to reverse the out edge? So let's say we want to reverse the out edge of the OR vertex. We're gonna slide one of the disks out, so one of the disks on the horizontal line out. That flips the edge inwards, and now we can flip the edge outwards. So when we are going to try to construct the gadget here, the space that was freed up by the disk moving outwards horizontally should be enough for the disk on the top to move in, right? And this is the same idea that is used to show squares as well, hardness for squares. Okay, so similarly for the end vertex, we need to move both of the disks out so that we can reverse the blue edge. So move the top disk inward. Okay, so one point that we need to be careful about is that the movement of the disks, we want it to be sort of discretized. We want it to to move disks to some discrete set of positions. What we don't want is moving a disk on one side a little bit, moving another disk a little bit, and freeing enough area for the top disk to move inwards, right? So this is bad. We don't want that. We somehow need a construction that will only allow us move disk inwards if the two disks on the input edges completely move outside. Okay, and for that, we are going to use the following wire gadget. And this is where we need actually disks of two sizes. Okay, so what happens here? Well, the disks are very tightly placed here. The wire corresponds to an edge pointing from left to right. If we move the right disk halfway to the outside, so all the way to its terminal position, then we leave enough space for it to move the other disks behind it, so that this tiny yellow disk can fit in the corner that was just freed up, and this movement can be propagated, and therefore in this way we flipped the direction of the edge. And this construction exactly prevents us from moving this disk partially. So suppose that we moved it almost all the way, but not exactly to the terminal position. This does not leave enough room for the yellow disk to enter this corner. And that means that the next big disk can move just a tiny bit, and the next yellow disk, there is nowhere to go, right? So only if we move the first disk all the way to its terminal position, we can flip the edge. Okay. And now that we have this wire, we can just put these wires together to make an OR vertex and an AND vertex. And they look very similar. The only difference here between them is in these corners. So you see in one case, we're hugging the disk tightly. In another case, there is a little bit more space and the corner looks more like the wire gadget construction. So for the OR vertex, what that means is that when we are flipping one of the input edges, both yellow disks can move to one side and thus free up enough space for the green disk on top to move inwards. And then for the end vertex, there's not enough space for two yellow disks to fit in. So they need to move left and right. So we have to move out both of the input disks. So basically that's the idea for the gadgets. And then the whole construction, putting things together, will start with some graph that consists of OR and vertices. We lay it out on the grid, and then we replace each vertex with a gadget. So this will be the view of the full construction. Okay, so to summarize this part, we have shown that multi-robot motion planning for disks of two sizes, and the difference in sizes is a factor of 2 here, in a polygonal domain with holes, use PSPACE-hard. The future work, the open problems here to consider is, of course, going to a single unit disk case. And also what happens if we only want to work in a simple polygon. So disks or squares in a simple polygon. What can we say about those, the hardness of those problems? And this will be the end of the part 1. Yeah, there's a question.
Yes. So what is the problem that you show hard now? So is it given a starting position and given an end position, whether you can move? Or?
I was not super clear about it. It's actually different. You can set it up in different ways. So you can start with a start position, start configuration, end configuration, check if you can reconfigure, or even deciding if you can move one robot from its starting position to some target position. That's also hard. So all the usual versions of the problems where you want to move all to all or one to any, or any to one, all of these are hard by the same construction.
Right, and that's the unlabeled case, right? Except
this is the two colored case, yeah.
And Irina, do you have any conjecture about these two open problems?
I think I may have some ideas for unit disk robots, but it's too early to actually say that that's a
say hard to show hardness.
Yes, yeah. Mm-hmm.
Okay.
But it's an idea that needs to be worked out.
Okay.
Okay. So now let me move on to part 2. And now I'm going to talk about actually developing algorithms for multi-robot motion planning for disk robots. And this work was initiated at a workshop where a lot of people came up with a lot of ideas and preliminary results. And I was not there, but later Kevin Buchen and I supervised a master's student, Stein Slot, who just graduated. And he has done a very good progress on the problem that was initiated at that workshop. So let me tell you about basically about your own work here. Okay, so moving on from hardness results to trying to develop algorithms, what makes these kind of problems hard? And all the hardness constructions, they pack the robots very densely. They use either robots of different shapes, different sizes, or also using polygonal domain with holes as the environment, right? So if we try to somehow get rid of all these properties, then maybe we can find algorithms. So we're not going to look at very densely placed robots. We're going to look at one robot size, and we're going to look at a simple polygon. Okay, and there's also some overview of the previous results. So the basically the initial work that led to this talk was done by people in this virtual room, where if we make an assumption that the starting positions and the end positions of the robots are well separated, and for unit disks where radius is 1 unit and the separation is 4 between the centers of the robots, then there always exists a solution to reconfigure robots from starting position to the final position in a simple polygon. Well, okay, you'll see that it's not always the case. There is not always a solution, but if there is a solution, then it can be found. And if there is no solution, it's very easy to see that there is no solution. So this was basically the initial work on which the following results were built up. There is also an extension of looking into producing more optimal schedules, where on top of the separation between locations of the robots, we added some minimum distance to the boundary of this location. But I'm not going to talk about optimizing the schedule today. We're going to just stick to figuring out, is there a way of reconfiguring the robots or not? So today I'm going to talk about producing an algorithm to reconfigure unit disk robots with tighter separation than just the separation of 4 units. Okay, so the original separation approach, I'm gonna quickly go over it just because we're building upon these ideas a lot. So we have at least distance 4 between centers of the start positions of the robot, and also target positions of the robot, and also between start and target positions. So again, in the brighter color, I show the initial position, and in the lighter color, the target positions here. Okay, so the usual trick of offsetting the boundary of the polygon to build the free space, and now we can only consider the center points of the robots. This is the moment where, as I said, you can easily see that there is no solution. So the robot on the left-hand side, cannot move through this narrow corridor, and thus there is no target location where it can end up in. So there is no solution in this case, but if the number of start and target positions in each component is equal, then there is always a solution, and it can be found by, well, we're going to construct this motion graph by connecting the locations to each other. And then using this motion graph, we're going to move the robots. Only moving from location to location each robot, right? So the whole motion will go from starting position to another, maybe starting position, maybe target position, but sort of moving along this purple graph. Okay. So there is this trick where even though you have multiple connected components of the free space here, they still can interfere. But the previous work shows that you can always find an order on these components in which you can process and move the robots within each one sort of separately. Okay, and within one component, a robot can always reach any destination because of the force separation. Okay, but now what we're going to do is we're going to look at different kinds of separation. So the monochromatic separation between two target positions and two starting positions, and bichromatic separation between start and target positions. And what we're going to do is we're going to keep the first one at 4 again, but we're going to try to reduce the second one. Okay, so first let me show you a construction why we cannot bring the monochromatic separation to lower than 4. So the separation between two start nodes and two target nodes. So here we have the two robots on the top of this construction, and then they want to move down the corridor to the two target locations. And the distance between the centers is just slightly less than 4. What that means is that when one robot, let's say, tries to get into this corridor to move downwards, it's not going to fit in because the other robot just slightly protruding into the corridor and blocks the way. And the same because the situation is completely symmetrical, if the other robot tries to move, no matter where these two are placed in the top part of this polygon, they cannot move down. They're blocking each other. So we cannot always find a solution for monochromatic separation less than 4. And there is another construction that, again, some of you may recognize, where we cannot always find a solution for bichromatic separation less than 3. So this is the separation between start and target nodes. So here the construction is the following. On the top, there is this circular arc corridor with a gap between the top and the bottom part of the polygon, just a bit less than the diameter of the robot, so that they cannot pass through. And the distance between the centers of the robots is just a bit less than 3. There is enough space for the bottom robot to move from its target, from its start to its target position, but the distance from this tip of the wall on the bottom to the ceiling of the top component is just below 4. So two robots cannot comfortably fit in there side by side. So what happens here is when one robot cannot move from one component to another. So we have a matching on the start and target positions. And if we try to move, let's say, the bottom robot to its target position, the top robot will always block it. The top robot, again, has a tiny bit of its side that is sticking from the top component into the bottom component. No matter where it is located, in its starting position, in its target position, or anywhere in between. Okay, so we cannot do better than monochromatic separation 4, or we cannot always do better than monochromatic separation 4 or bichromatic separation of 3. So that's going to be our goal for today, to develop an algorithm to achieve finding a schedule for these two values, 4 and 3. But we will start first with a simple case of a single free space component. So when there is a single free space component, so here we had two free space components, right? Because the top component would be separated from the bottom component. But if we only have one, then we actually don't have this blocking situation. And beta, the bichromatic separation, can even be 0. But the monochromatic will still be 4. And then we will extend it to the case of multiple free space components. Okay, and the general approach is very similar to the previous work, with slight modifications for the cases, for the bad cases that arise where the bichromatic separation is not large enough. Okay, so the idea here is that we are still going to only move robots from on start and target positions. And we're going to construct the motion graph on the start and target positions. So use that to navigate the robot. So that's similar to the previous approach. And the motion graph is a graph that has all the starting and target positions as nodes. And we will connect those nodes that we can route between, right, in some way. So for example, this is one way that we could construct a motion graph here. So that's how it would look like. And then we're going to do a pebble game where we place pebbles in the start positions and we move pebbles one by one so that all the target positions are eventually occupied. So we can move that one there, that one there. And now let's say we want to move the bottom one to the top empty slot, but it's obstructed by another pebble. So we'll move that one first and then the other one. Okay, so something important to note here is that we want this path between the two nodes to be unobstructed by other robots. And here we're gonna define an aura of a robot, which is just the disk of radius 2 centered at the center of the robot. So if any robot intrudes into an aura of another robot, that means that they intersect. So the path between two nodes, we don't want them to pass through a third aura. Otherwise, we cannot guarantee that there will be a proper path between the two nodes that we want to navigate the robot. Okay, but so now because beta is less than 4, we can have this very specific bet situation where, let's say we want to move robot S1 anywhere into any of the locations that are given by the motion graph, which can be S2, T1, or T2. And in any case, the path that we are trying to move along passes through a third aura. So here, if we're moving robot from position S1 to position S2, and there was another robot in T1, there would be a collision, right? Similarly, we cannot move S1 to T1, and we also cannot move S1 to T2 because it passes through 2 auras of 2 other locations. So this is the case that did not arise before, and this is what we're going to try to solve. So we cannot simply create a connected motion graph. If we connect the neighboring nodes in whatever way, at some point, depending on the configuration, we may or may not have an edge in this graph. Okay, so what we're gonna do here is the following. We are gonna define this blocking area. So this is the bad part of a narrow corridor in the free space that blocks us passing, let's say, from one corner of the free space into another. So a blocking area is defined for a target position. It will be disconnected from the target position by other auras. For example, so the red region here is the blocking area, and the aura of this start position on top, it disconnects it from the center of TI. And this blocking area splits the free space component into two or more pieces. And now what happens is if we are going to try to navigate towards TI from the other side, from the other piece of the free space component, then all the paths will go through this blocking area, and we cannot guarantee that there will be no collisions. Okay, so how can we deal with this? Well, we'll simply remember that some of the edges in our motion graph are blockable edges. They may be blocked, but if there is a robot in a target, in the corresponding target location, and we'll have to somehow fix it, make it work. Okay, let's see how we're gonna deal with it. So this is the whole construction. We start with, recall we're still in one free space component. We have the same, we subtract the auras of the start positions from the free space. This may have separated the free space into multiple components. So let's look at one component for now. For each location, that is, whose aura intersects the boundary of the resulting remainder of the free space, we're going to choose some representative point. And what that means is just if we are going to go around the resulting boundary, we're going to go through all these representative points so that we can connect them in that order. And for those nodes that do not whose aura does not intersect the boundary of the resulting free space component, we will simply shoot a ray upwards. So this is again similar ideas from the previous algorithm. And either we hit the boundary and then we place the representative point there, or we hit an aura of another robot and then we just connect those two nodes in the graph. So we create now edges between all locations in the order along the boundary. And if some vertical rays hit the auras of other locations, we connect those with an edge. And this is the motion graph that we construct for the example on the right-hand side. Okay. So when we want to navigate from one location to another, we will just follow these paths that we created from the node to its representative point, then along the boundary, and then to the target location. So for example, in blue highlighted on the left-hand side in the motion graph, that moving from one node across this edge to another node corresponds to moving along this, let's say, flipped gamma-shaped path on the right-hand side. Now, back to blocking areas and how are we gonna deal with those? So here we don't have any blocking areas, and thus we can build this motion graph, and none of the edges are obstructed here in any case. But if we do have blocking areas, then we can build this motion graph in the different components on each side of the blocking area. And now we want to connect those components of the motion graph. And the way that we do it is we're going to connect the start node that contributes to the creation of this blocking area to the blocking area, and then clockwise and counterclockwise to the nearest nodes on the other side of the blocking area. So here we would create these two red edges. So we connect S1 to T1 as the traversing clockwise the area on the other side of the blocking area, and S1, S2 the other direction. Okay, so now what we would do is we're going to try to match starting positions to target positions and hope that we can successfully navigate them. And if something bad happens, like there is a blocking, then we're going to try to move away the robots from the blocking area so that others can pass. But unfortunately, if we just simply arbitrarily choose pairing between starting and target locations, we can get cyclical blocking. For example, here, if we matched S3 to T2 and S2 to T1, and somehow ignored that there is this robot S1 in the middle that can move to either of these target locations, then we're going to be in trouble. If we move, let's say, S3 to T2, then it activates the blocking area on the right-hand side, and the robot S2 is stuck in there. And the same thing happens if robot S2 moves first. So not all matchings will be valid for us. So we will need to fix it. And we could be fixing them by somehow uncrossing different matchings. But there is a better approach. So let me tell you about this better approach. We're going to build a couple of, we'll build another graph and see if that will help us. So now there's an example of some free space area with two blocking areas defined by the two target locations on the left and on the right. Then let's define these residual components. So we take the free space, we subtract all the blocking areas, and we see what the free space fall apart into. So into multiple connected components, and we call them residual components. And now we build a graph on these residual components. So we call it a blocking area graph. We're going to connect the nodes corresponding to the residual components by a directed edge, and the edge will be directed from a node that has higher number of starting positions minus the number of target positions. For example, in the drawing, we have the leftmost component. It has one start position and 0 target positions. So the weight of this component is 1. In the middle, we have 2 start and 2 target locations. So the total weight is 0. And on the right-hand side, the weight is -1. So the edges will be directed from higher value to the lower value. And we're going to process this in the order according to where the edges are pointing. So what we can show is the blocking area is connected, blocking area graph is connected and is a tree. And now approach here is to solve each of these components recursively. If we can split the problem into 2 subproblems so that the number of start positions and target positions on both sides match, then we just do that. And if not, we'll just take a sink. A sink means that there is more target positions than starting positions, and the sink is easier to solve. So then we solve the sink and see what happens next. So let me show an example of what's going on here. So we have this free space component with some start and target locations, some blocking area, and we build this motion graph with some edges crossing the blocking areas, and that's why they're highlighted in red. And we have the blocking area graph on the 3 residual components that we get. The weights are 1 in the leftmost component, -1 in the bigger part, and 0 in the tiny component on the bottom right. So now what we said we're going to see if we can split this into two pieces where the number of start and target locations match. And indeed, this we can split along this edge here. So we do that. We deleted the two red edges from the motion graph. Okay, that's good. So now we can solve a sink. So let's solve this sink with weight -1. We're gonna start moving these pebbles from, or robots from some start locations within the component to target locations. Okay. And now we want to move this start robot from a start position across the blocking area to even out the number of start and target locations in each component. Let's say the number of robots needs to match the number of target location in each component. And we see that the red edge is currently blocked. There is a robot present in the location of this target position. So we'll just move it away. And we have a surplus of target locations, so we can always move it away. So we move it away, and now we unblocked this red edge. We can move the robot along it and balance out the weights on the nodes. So now we are left with one component unsolved, which is easy to solve, and we are done. So this is the general approach how solving it. Again, because the blocking area graph is a tree, we can always start with either splitting it into smaller pieces or with a component that has more target locations that currently robots are present in there. Okay, so this was bichromatic separation 2 actually, and I did not explicitly state that, but in all the pictures I showed that start position and the target position, the robots don't overlap, right? So that was beta 2 implicitly, but it doesn't really, it's not that difficult to extend it to beta equals 0. The way we do it is just a simple observation. If if a robot has some start position as I overlaps with a robot at some target position Tj, then these two robots cannot intersect anything else. So they're just going to be one pair of robots. Any third robot getting closer to this pair would get too close to either start node or target node and violate the monochromatic separation of 4. And in this case, we're just going to ignore that there exists this target position Tj. We're going to treat Si as at the same time the start and the target position. And then all the way at the end of the algorithm, we'll remember that Tj existed and we'll move the robot from Si to Tj. So that's not a difficult extension. And now in the following, I guess, 3 minutes, I'll show you, or maybe even less, how to extend this to multiple free space components. And again, we're not inventing anything new here. Well, first, let me explain why the multiple free space components may be difficult. So the robots between different free space components can interfere. For example, if there would be a robot in the position Tj in the figure, the robot Sk cannot move across the bottom part to its target location, right? It's a similar idea as this example of beta less than 3 blocking. So the robots can interfere, but because we have now beta at least 3, we cannot make it such that both the starting position and the target position both interfere with another free space component at the same time. So if beta is greater or equal than 3, then if there is a robot in Tj, we could undo some of the moves until it's freed up. And we can build again a graph on free space components now. And again, this graph will be a tree. We can add a edge direction from one component to another component, depending on how interference happens between the starting node or between the target node and another component. And then we will again solve the free space components in some order according to the topological order we get from this tree. And that would make a general algorithm for mu equals 4, monochromatic separation 4, and bichromatic separation 3. So let me go over again what I've talked about in part 2. So first, the lower bounds, we cannot always guarantee that there is a solution for monochromatic separation less than 4 or bichromatic separation less than 3. If we are lucky enough to only have single free space component in our case, in our construction, then we can simply forget about beta and make it 0. But if we have multiple free space components, then we can show that there is always a solution for mu equals 4 and beta equals 3, and we can find such a solution. And now again, let me list open problems, but okay, here it's going to be one. Yeah, so now again, if we add holes to the polygonal domain, what happens then? Right? Can we make the other bounds a bit tighter? Okay, so finally, let me just conclude with the general observations that if we have a multi-robot motion planning situation where robots are of different sizes or different shapes, they are densely packed in a polygon with holes, then most probably the problem is hard and we cannot solve it. But if the robots are all the same, nicely shaped, they're well separated, and in a simple polygon, then we can check if there is always a solution, and we can find it. And exploring this area in between these two cases is the remainder of what needs to be done to completely explore the area of multi-robot motion planning. Thank you.
Thank you very much, Irina. You know you can clap your hands. Other questions to Irina? We don't have much time, but if we can take one quick question. Anybody? Okay, so thank you again, Irina. Let me just advertise the talk for next week, if I find it on my. So next week we have Florian Pocconi, who will talk about some methods for reasoning about topology and global geometry in machine learning and robotics. Stay safe and healthy and have a good week. See you hopefully next week.